Alrighty, time to get ourselves started here. I'm going to finish up by talking a little bit about angular momentum, only like 3 slides on that. And then we'll get into our new, what do they call them in this textbook, units. It has five of these things, and we're ready to start the second one. So, oh man, it's a good thing I didn't have a quiz today. I was totally going to have a quiz and forgot, and it would have been really bad for all of us since it's like only the second time he's been late. If I had a quiz, that would be bad. So I'm glad I don't. So let's start with what angular momentum is. And to understand angular momentum, I really should start with what linear momentum is. Now, football season hasn't started yet, and there's no other sport that really matters. So I know that's not true. Soccer, okay. So right now, Man City has some momentum going on.
Whoa. Hold on.
They have the Derby this weekend. Granted, we won't have Sergio playing, but you know.
We'll get you.
Yeah, we'll see. Who do you like? They're in a different league. We're in the same Champions League group, though. And we're going to steal your goalie, or if we haven't already. Okay.
That's how Man City wins. That's how the teams always work.
I know, they've got money. Okay, but what does momentum mean? If I say that Manchester City and Manchester United and Chelsea all have a lot of momentum, I have at least 2 other people who know what I mean. Okay.
Why are you giving Chelsea?
Huh?
Why are you giving Chelsea?
Because they're also undefeated.
Yeah.
This is bad as Man
I'm paying attention, man. I'm trying to be a fan. Okay, so Yari understands. So tell us, Yari, if I say these teams have momentum, what am I really saying?
That they're doing good.
They're moving forward.
They're moving forward. They're on a roll. And they're going to be hard to stop. That's what momentum is. So if something is moving, it's going to be hard to stop. We say it has momentum. If it's going to be easy to stop, well, it doesn't have momentum. So, Man United. Okay, we'll see at the Derby, man. I should talk. You talk before the game, you can eat crow. You talk after the game, you should. Okay. So momentum is a measurement of how easy or hard it's going to be to stop something. More momentum, harder to stop it. Angular momentum, also known as rotational momentum, is the same idea, but it's about rotation. Now, one thing that you may or may not know is when we talked about inertia, we measure inertia by measuring how much mass something has. And inertia was the propensity to stay in constant motion. So something with more mass is going to have more of the inertia, which means when it's moving, it's going to have more momentum. And so momentum, linear momentum, is just the mass of the object times this velocity. So if, for instance, Chione and I were running at the same speed, I've got to weigh twice what Chione does, which means I have at least twice his mass. So if we're running the same speed, which one of us has more momentum? And the easy way to answer if you had no other judgment is just to ask yourself, which one would I rather tackle? Richard or Chione if they're running the same speed at me? And what's the answer? You'd rather tackle Chione because he has less momentum, less difficulty stopping. I have more momentum, more difficulty stopping because I have more mass for the same speed. Now, if Chione has half my mass, but he's running twice as fast, then it's about the same. Exactly. So the rotational equivalent is how easy is it going to stop something from rotating? Now, let me tell you about the world's worst safety lesson I had. When I was in graduate school, I was starting in a research group, and we had a machine shop where we worked on preparing our experiments. And the technical dude in our lab took me to a safety thing to make sure that I wouldn't hurt myself. And we get to the drill press, showing me how to do it. And he says, now never grab the chuck with your hand to stop it. And I chuckled because apparently that's a downfall. People think I'm being disrespectful when I laugh at things I find funny. Because I'm not supposed to find them funny or something. Anyway, he said, no, there's some things where it's safe to grab the chuck. For instance, with the lathe, if you have it on the belt drive and you disengage the belt, then it doesn't have much angular momentum, and you can grab it with your hand and you'll be okay. Let me show you. And so he makes sure it's not on the gear drive, it's on the belt drive, spins it up, disengages the belt, and grabs the chuck. Only one thing he didn't pay attention to was the chuck. The chuck, of course, is a circle, and it has these teeth that you move in and out to hold it. Hold whatever actually it's only 3 teeth on that one, I think. And these teeth at that point were extending out like this. So when he grabbed it, he had those teeth sticking out. It just ripped up his hand. Now, it would have been relatively safe if he had low friction on it, but he couldn't just stop it instantly with his hand, and instead his hand got torn up. And so he went to the emergency room, and I was cleared to work in the lab. That was safe. So angular momentum is that propensity to rotate. And just like linear momentum, it has to do with the mass. But it has one thing different than linear momentum. The position of the mass matters. Right? With our linear momentum, when I'm running, it doesn't matter if my stomach is heavy or if my legs are heavy. I've got that weight, and I'm going to have the same momentum. But when something's rotating, if the mass is close to the center of rotation, it doesn't make as much difference. If it's farther out, it makes a much bigger difference. So angular momentum has that equation, mass times velocity times the radius at which the mass is around the center of rotation. So as an example, I have these two 5-kilogram masses. And so if I take these two 5-kilogram masses and I hold them here next to my body, the radius is pretty small. So they're not going to make a very big difference for my rotational inertia, which is what we call it. My angular momentum is not going to have much dependence on these masses. But if I hold them out at arm's length, now they're much farther away to have a much bigger effect.
It's like spearheads.
It's what?
Spearheads.
Like spearheads?
On the spear. On the spear, you know how that's 2 heads?
No.
It's easy to knock the spear around the head.
Okay, I'm going to, rather than have you explain it to me and me still be confused, I'm going to do my demonstration here. So who wants to be my demonstrator who's going to sit and spin? Okay, come on up, Alden. So I'm going to have Alden do a quick little demonstration of how angular momentum works. Actually, I think you have less chance of your hand saying something if you come up here.
Can I also raise the chair a little bit?
You can put the chair wherever you want, buddy. It's yours. Okay, so you're going to hold this in your hands. And I put my fingers in the things to give you a better grip. Okay, so we're going to start by me just rotating around. He's holding them, hold them right next to your chest. So he's holding them in. Now we're going to have just take your hands out, put your arms like. What happened when he did that? Slow down, bring back in. Now, of course, you know it's a lot more fun. Put them out again.
Oh, gosh. You're lucky I don't
Now you pull them in.
You're lucky I don't get dizzy.
Okay. No, now go ahead and put them out. And now try to walk back to your desk. Because, that's always the best part. Okay, what was going on there? When he brought his hands in, what happened to his rate of rotation? It increased. When he put them out, it decreased. The reason why is that angular momentum is going to be conserved if there's no torque. A torque is a force that's trying to change the rotation. We didn't have any forces trying to change his rotation. Any forces trying to change his rotation, so his angular momentum stayed the same. But when he brought the radius in, then the right side of that equation, m times v times r, went down. But for the entire thing to stay the same, something has to go up, and the mass can't go up. So the speed at which they were going around went up. This actually explains what's happening with the orbits of planets. When they're closer to the sun, their radius is smaller and their speed has to pick up to have the same angular momentum. So we learned it before from Kepler's laws. Then we saw from Newton's laws that we can come up with the equation for it. Of course, I didn't do an equation for how the speed of a single orbit varies. But angular momentum explains why when things are close to the sun, when planets are close to the sun, they go faster. When they're farther away in the same orbit, they go slower. So angular momentum becomes another big thing in astronomy because it allows us to, I don't know why, don't tear up your hand. It allows us to understand how speed should change when things get closer and farther from mass. Any questions about that angular momentum? I think I got like 2 more slides, but I probably covered everything on this one. No questions? Okay. Yes, demonstrations are always good, but we already had them. I usually pretend I'm an ice skater and do a little spin, pull my arms in and spin faster. We just finished the Summer Olympics. In fact, I have a DVR, and I just finished the Summer Olympics on Monday. And in diving, that's an area where you see people manipulating their bodies to change how fast they rotate. When you have somebody diving, if they're spread out like this, going forward, like that, they're going to have a slow rotation. But if they tuck, they brought that mass in, and if they're going to have the same angular momentum, mass closer, what has to happen to the rotational speed? Has to speed up. So you see that in diving, you see that during the Winter Olympics, in ice skating, in the ski jumping competitions. Whenever you're trying to do something where you want to control rotation, you change your body where the mass is. And if you've ever watched ski jumpers who are doing their tricks, beforehand they'll be going through and you'll see them going, and you're like, what kind of semaphore is this? Well, they're moving their arms around to change the distribution of mass, to change how they rotate under constant angular momentum. And so when you see them just standing, you're like, that doesn't make any sense. But when they're rotating, you could actually watch where the hand goes out here, comes in here, goes there, and you can see how it's affecting the rotation at a time because they want to end up on their skis, it turns out. Okay, clicker question. And we have, everybody should have a clicker, but Connor, it still says yours isn't registered. And so it won't let me see your scores until it's registered. You can record them, but I can't see them until registered. It was a his today. I missed my gender equality on one of them. Got it clear, Jessica? It says you haven't answered yet. There we go. Okay, so we had, I forgot to remove that little icon, sorry. Okay, 11 people said when the student extends the arms, they slow down. And we just saw it with Aldwin. That was correct. Now, a bigger, more important question is why? Why did Aldwin slow down when he extended his arms out?
They had more air resistance.
Not more air resistance, because he sped up when he brought him back in.
It's spread on my mass.
Okay, the mass was farther out, and so because the angular momentum is going to stay the same, there's nothing trying to change his rotation. No. I wasn't pushing on him. There was very little friction in the rotating chair. Angular momentum stayed the same, but angular momentum is the mass times the velocity times the distance. So if the distance goes out, the velocity has to go down to keep the same total number. So it's for conservation of angular momentum is the actual physics lingo. Conservation, not changing. Angular momentum, that propensity to maintain in constant rotation. Okay, so that finishes up the material from Unit 1, or whatever it's called, Part 1, something 1. Now we're going to Part 2, which is more physics. But we're going to start talking about light here. But to understand light, we actually have to understand some things about atoms. So, a very quick background of our understanding of matter. If you go back to Democritus, he believed that if I took a chunk, so I'll take this chunk, I cut it into 2 pieces, I'll have 2 smaller pieces. Very astute gentleman. But then he said if I take one of those and cut it in half, I'll have 2 smaller pieces. And if I keep going, I'll eventually get to the point where I simply can't cut it in half anymore. And at that point, I'll have the smallest piece possible, which he named atom for the Greek word that means indivisible. I like it. We're being justice for all. So that's what atom actually means, is indivisible. It was Democritus' idea. You break it down, you'll finally get to the smallest piece that you can't divide anymore. And then in 1897, J.J. Thomson made an observation. That is, they had what they called cathode rays. When you had a cathode and anode, they saw these things coming out of the cathode. And he studied them and found that they turned out to be negatively charged particles, what we now call electrons. And he said, well, they came out of the cathode, so the cathode must have had electrons in it. And so I must have 2 kinds of things: the electrons that are being pulled out, and something else. And so he theorized that something else was just kind of a slurry of positive charge. Electrons were negative, so it would be a slurry of positive charge. So we have an overall net charge of 0. And so it was called the plum pudding model. I don't eat plum pudding. It means nothing to me. So I like to call it the oatmeal with raisins model, where the oatmeal or the plum pudding, the pudding part, is just your positive charge spread out everywhere uniformly. And then the electrons are the raisins. And so that's what J.J. Thomson proposed is what matter is made out of. Well, that was in 1897. 12 years later, you had a great experiment, not done by Ernest Rutherford, but done by Marsden, who was like the newbie in the lab. The way I understand the story, there was Rutherford, who was the head of the lab, and then he had his trusty sidekick, Geiger, who you might have heard of, Geiger, Mueller counter, that Geiger. And then they had the new guy, Marsden. And Geiger comes to Rutherford and says, I think young Marsden here is ready to do an experiment on his own. Let's let him try something, spread his wings and fly. And so Rutherford says, well, here's an experiment I've been wanting to do. They were studying radioactive particles. And he said, let's take gold. Gold is malleable. That means you can hit it with a mallet. Instead of fracturing, it just squishes. And so you can pound gold so it's really thin. So let's make a really, really thin sheet of gold and then have Marsden shoot alpha particles. They're basically helium nuclei. Shoot these helium nuclei. They didn't know what a helium nucleus was back then. Shoot them at this gold film and see what happens. And what he expected was, well, based on that plum pudding model, if it hits an electron, because it's so much more massive than an electron, it'll probably slow down just a little. And if it doesn't hit an electron, it'll just go through. Once again, maybe a small deviation if it hits an electron, not much at all. And virtually no change if it doesn't hit an electron, just come through and slow down a little. So they give it to Marsden, his first experiment all on his own. And Marsden does the experiment, and he finds it's completely different than it was anticipated. Remember, we're talking about scientific method in this class. They had, based on the model of the plum pudding model, they took a prediction of that, and we should call it a hypothesis because it was a model with a, plum pudding model is the model, but the hypothesis that led up to it is what they're studying. It predicted a certain outcome. And then they did an experiment to test that outcome. and they got something completely different. If you get something completely different, now it's a newbie in the lab, you probably say, dude, you sure you did it right? But what do you do in the scientific method if you get something that says, no, your hypothesis was wrong? You go back and you change your hypothesis because you have new information. So now they had new information. Their new information said that when you have these alpha particles coming and hitting that gold, most of them went through absolutely unchanged. No change whatsoever. But some of them went off at crazy angles, some bounced straight back. Now think about this. The electron was less than, about 1,000. I can't remember the ratio. Somewhere in the ballpark of 1/1,000th the mass of the alpha particle. So we might compare that to a BB and a wrecking ball. So if I have a wrecking ball, the alpha particle comes and it hits the BB, how likely is it that the wrecking ball bounces back off of it? That's just not going to happen. When he went on the speaking circuit to talk about what he discovered, Rutherford said it was like if you fire a cannonball at a piece of toilet paper, and when the cannonball hits the toilet paper, it bounces back at you. You know, they were just shocked. And so they said, well, it must not have hit something that was like, a wrecking ball hitting a BB. It must have been the other way around, like, a bowling ball hitting the wrecking ball, and the bowling ball bounces off of the wrecking ball. You guys know what a wrecking ball is, right? Yeah. When I was a kid, they tore down the gym at NBA with a wrecking ball. It was awesome. So he said there must be something really massive at the center and then mostly empty space. And so he said, I know, it's like astronomy. It's like you have the sun at the center of the solar system, and then you have the planets doing roughly circular orbits around it. And so he said that must be what an atom is like, with a core at the center that he called the nucleus that has almost all of the mass, and then the electrons doing circles around it. And so it's called the planetary model because his new hypothesis was explained by looking at how the planets work. Well, right away, there were problems found with that model. Niels Bohr came over from Denmark to work with Rutherford, and just a couple years later there, you see that Bohr came up with a new model. What were the problems with the old model? One problem with the old model Rutherford's model, was that Rutherford said that the electrons are orbiting in circles like planets orbit the sun. Planets can orbit the sun at any distance. And what that translates into is having any amount of energy. And so Rutherford's model said that the electrons can have any amount of energy. But you guys have seen a neon light before? Actually, it'd take me 5 minutes there if you'd set up, so I'm not going to bring one out right now. I should have thought to bring it out before. Instead, I'll bring it out on Friday. But we'll look at a lamp, and what you see is only very specific colors, not a continuous range of colors. And those colors have to do with the energy levels of the electrons. So if you could have any electric energy of an electron, you would have colors covering the entire gamut coming out of your neon lamp.
So you need white light. So you need white.
Yes. Yes. We'll see that on Friday when I bring out the demonstration stuff. And so that's not what they saw. And so they knew there was a problem there. There's also another very basic, above the level of this class. When you have a charged particle and it accelerates, if something goes in a circle, it's accelerating because it's changing direction. If you have a charged particle that's accelerating, it has to give off radiation, which means it's giving off energy and slowing down. And so with the Rutherford model, you should have no electron orbit for more than 1/1000th of a second before it crashes into the nucleus. That's a failure. And so Bohr came up with a quantum model. Quantum, right? I mean, this is a lot of physics to take in. There's only a small amount that I know you're going to be able to keep. But quantum is really an important piece of this. quantum model says there are only certain energy levels that the electrons can have. And so the light that we see when we look at the neon light is the light that matches the gaps between the energy levels the electrons can have. And so that quantization, the saying that there's only certain steps available, explains why we have the discrete energy levels in a neon light instead of the white light, a continuous range of light coming out of it. Of course, the quantum model itself was flawed. The quantum model suggested that you should have, basically the amount in each level would be the most and the lowest energy level, and then some, fewer, the next higher, and so on. But when you observe, that's not the way it turns out. And so now we have what we call the standard model, which is more complicated still, but based on the quantum model. As far as you guys are concerned, we'll just stick with the quantum model and just say the standard model is just moving forward from Bohr's quantum model. So what are the important things about this quantum model? Number one is those discrete energy levels. I always try to liken it to having shelves in a closet. And you can have your shoes on the bottom shelf or on the next bottom shelf, the third bottom shelf, but you can't have your your shoes on the 2.6315 shelf because it doesn't exist. And that's what the quantum model is saying. There's only certain energy levels where the electrons can be. A second thing that I didn't mention is the quantum model says we have no clue, no idea in the world what electrons are doing in an atom. We don't know where they are or where they're going. We can calculate where they're likely to be, but we don't know where they are. And so instead of going with what the Bohr model had said, Rutherford's planetary model had circular orbits, the Bohr model still has circular orbits. The standard model that we use today, which is still a quantum model, says that we have no clue where the electrons are. We have no clue what shape their orbits are. But we can calculate where they're likely to be found. So you see those pictures of an S orbital, and it looks like a circle. It's saying that it has like a 97% chance of being somewhere inside that circle. And you see a P orbital that looks kind of like a figure 8. Once again, it just has a high probability of being somewhere in that shape. Not on the line, but somewhere within. So that's what we understand about atoms today. So here is a picture, instead of shelves, it's showing levels in a building to describe those energy levels in an atom. And electrons can be at, and notice these are kind of fuzzy. That's to indicate that there's not a circle where the electrons are. It's just where they're likely to be. So the lowest energy level possible is called the ground level. And we use N to indicate the level. It's actually called the principal quantum number. And if N equals 1, that's the lowest possible energy state, so we call it the ground level. Just like if you're in a building, right here, we're in the ground level. When I was at PUC, they built the science building back when I was in high school, but they didn't finish it until I started teaching, a gap of some 12 years. And when they finished it, they put administration on the bottom floor. And it had been first floor, the second floor, and then this was the basement. They couldn't call it the basement, so they called it the garden level. But normally you consider the lowest floor the ground level, right? And basements below that. So the ground level, the lowest floor, the lowest energy level electron can have, and then you have the excited states, the energies that are higher. So this axis here is representing energy. And so if you have an electron that's up here, it could conceivably fall and either land there or land there. It can't fall and stop somewhere in between the shelves. It'd have to land, or in between the floors, it'd have to land on one of the floors. And so, of course, the one that goes from the third level to the first level has a bigger drop. That represents a bigger drop in energy. And that energy difference goes off in the form of light. And so the way we draw this in the form of light is we draw a squiggly line like this, and that's the light coming off. And so this is a higher energy light if it goes from 3 to 1. It's a lower energy light if it goes from 3 to 2. Yes?
Does that affect the colors? It's like some
Yes, it does. And in fact, where is it? Okay, I don't know where the equation is. It's coming up, and I'll write it here. The energy difference is equal to the energy of a particle of light, what we call a photon, which is just equal to a constant multiplied by the frequency. So in a few minutes, we'll have a spectrum of light showing the frequencies or the wavelengths. And the higher the energy, the higher the frequency of the light. Higher frequency means more bluish, lower frequency more reddish for visible light. So that's exactly right. Different color for the different energies. So in this case here, going from 3 to 2 might have been red light, and going from 3 to 1 might have been blue light. I shouldn't have used violet because violet is actually higher energy than blue. So let's change that to red. There, that matches reality. Let me take a break to inform you of why I'm going over this detail about atoms. I am pretty sure nobody signs up for this class and says, yeah, I'm going to learn about atoms and how they work, right? Hannah was not thinking that at the very least. What is the one measurement we make for virtually all of our information in astronomy? We are looking at light coming from things out there. So analyzing light is primarily what we do in astronomy. It's about the only thing we can do to learn about anything beyond our solar system. And so when we make measurements of light, we need to know how to interpret it. Well, how do we know how to interpret that light? We look at what we can learn about light from here on Earth, and then we take the physics that we learned here on Earth, and we use an assumption that's called universality. That assumption of universality is that the laws of physics that we have here on Earth today are the laws of physics everywhere in the universe at all times. And so if we observe something works this way on Earth, we then, with that assumption of universality, say it's going to work that way everywhere else. So I observe this light from this location, and it must be this that it means. So all of this is so we can interpret the light that we receive from astronomy. You know, it's a really big point because how do we know what we think we know? It's built on, I don't want to say it's on a house of cards, but it's built on one piece of knowledge and another piece and another piece. And if one of those pieces is wrong, then all of our conclusions thereafter are going to be wrong. So we need to have some understanding of where this comes from and not just say, yeah, pretty light. It must mean what the scientists say. So that's why we're learning about this, so we can understand where the ideas come from when we talk about, so we saw, you know, at the last slide for today's presentation, which I'm not going to get to, has a breakdown of the chemical elements in the photosphere of the sun. Well, no one's gone to the photosphere of the sun, they can't survive, right, to collect them and analyze them. But what we can do is we can see the different colors that tell us about these energy levels, and then from knowing about those energy levels, we can say, well, on Earth, this set of energy levels means iron. And we can determine what the elements are. So it's based on this. Now, if we talk about the structure of an atom, the nucleus has a certain number of protons in it that we call the atomic number. It has the symbol Z for atomic number. So Z, the atomic number, is the number of protons in the nucleus. That atomic number is really important. That atomic number is what sets the energy levels. So if you have, look back there at the chart, we have, for instance, oxygen there. an oxygen in the top right corner of the box, it has an 8. That tells you that it has 8 protons in the nucleus. Now, if you look down below the O, you see another number that I can't read from here because I'm not wearing my glasses, but it's somewhere close to 16. What is the number? Somebody who actually can read it.
15.9994.
15.9994? Okay, very close to 16. That's called the atomic mass there at the bottom center. And that's telling us that the mass, how much matter is present in an oxygen atom. So if it has 7 protons, each proton has a mass of approximately 1 atomic mass unit. U is the symbol we use for atomic mass unit. So oxygen with 8 protons has 8 atomic mass units worth of protons. But it also has in the nucleus another thing. What's the other thing in the nucleus? It was not proposed until a while after the idea of protons, and that is neutrons. Protons are little positively charged things. Neutrons have no electric charge, but otherwise they're just like a proton. So you have neutrons in the nucleus as well. So the nucleus has both proton, well, yeah, it doesn't say it here, has both protons and neutrons. And neutrons also have an atomic mass of 1. So if we look there and we say, okay, so it has a total atomic mass of oxygen of 16, and it has 8 protons, 16 minus 8 leaves me a remainder of 8, so it must also have 8 neutrons. So the oxygen nucleus is 8 protons and 8 neutrons. But of course, that wasn't an integer. There are 2 reasons it's not an integer. Well, 3 reasons it's not an integer. Reason number 1 is not all oxygen has 8 neutrons. You can have different numbers of neutrons. If I use carbon, I actually know the numbers possible for carbon. Carbon has 6 protons. It can be stable with 5 neutrons or 6 neutrons or 7 neutrons. You can also have unstable forms with like 8 neutrons or 4 neutrons, but they're unstable, they're radioactive. Those different numbers of neutrons make a very tiny effect on the energy levels of the electrons. It's the protons that basically tell you the energy level. So when we talk about elements, it's the protons that tell us the element. Any element that has 8 protons has to be oxygen. Doesn't matter the number of neutrons, it's still going to be oxygen. So that atomic number tells us the behavior. The atomic mass tells us how much is there. We have electron orbitals. We don't know what they're doing. We just know they're orbiting. And they have different energies. So if I have an atom and I have, let's take this picture here. It says we have an electron that's in the n equals 2 state. That's the first excited state because n equals 1 is the ground state. If I have light come through and this light has exactly the energy necessary to go from 2 to 3, it will be absorbed. If it has any different energy, it'll just go through. So I can shine white light on my neon gas, and only certain colors will be absorbed because those colors correspond to the gaps between available energy levels. So we call that an absorption spectrum, where you have light absorbed matching the gaps between energy levels. Now, of course, when the electrons go to higher energy level, they can fall down and give off light. We call that emission. But once again, it has to have energy equal to the gaps. So the energy emitted is exactly the same spectrum as the energy absorbed. Now, there's some other quantum physics rules that make some more likely than others. But absorption occurs when light comes in with just the right frequency to be absorbed by an electron. The electron goes to a higher energy level, and all of the energy of that light is gobbled up. So that's what absorption is. Emission, just the opposite. It falls back down and gives off the same frequency if it's going to go through the same 2 levels. Okay, question to see if you recall anything, because I know I went through a lot. I know this. So which model or models, so that means you enter all that you believe are correct and then hit enter, held that atoms did circular orbits about the nucleus? All right. Everyone's answered. We had 2, 6, 9, and 4. Now I want you to discuss amongst your friends, and then Connor's going to tell everyone after we repoll what he came up with.
Because boards on the seven.
Well, I mean, I wasn't sure that was. I was trying to think I think most of it I wasn't sure if it was C or not. I wasn't sure if it was C or not, but I just yeah, I'm pretty sure it's because that's so yeah.
No problem, man.
Yeah.
You guys talk about yourself.
Michelle.
Yeah, me too.
I can tell you.
Okay, let's go ahead and re-poll it. This time I'll help you out a little bit by letting you know that there are 2 correct answers.
Using this, it's fine.
Waiting for Aldwin and Amelia to answer second time.
Oh, answer second time, yeah.
Okay. You ready for this, Connor? Yeah. Okay. This time around, we had still 2 people with Thompsons. 9, 12, and 1. Okay, Connor, explain to us, first of all, which one, or well, I told you it was 2, so which ones did you answer and your reasons?
Well, I originally picked C for sure, especially when listening to the collection and all that. But then after that, it was like, it's either like B or D. And I think I went ahead and guessed the second one was D. But C for sure.
Okay. C for sure, and then he guessed with D. And you're right, C for sure. Bohr went with the circle, but Bohr wasn't the one who came up with the circle. Who came up with the circle? And that open to everyone, not just to Connor. Okay, Rutherford was the one that came up with the circle based on planets. Now, at this time, I think it was already known that planets did elliptical orbits, but nonetheless, he went with circular orbits. And so you have circular orbits for those 2. So if you have electrons doing circular orbits for those 2, what was believed before this? What was the plum pudding model for electrons? What were they doing? Actually, that's the positive charge that was spread out. The positive charge was like the plum pudding, the pudding part, or the oatmeal in my oatmeal and raisins, spread out, and the electrons were the raisins. So they were just sitting. Here's one, here's one, here's one. They were just sitting there. That was the model with the plum pudding, that the electrons were just sitting there. And what about the standard model? I've tried everything to make it so it won't give me reminders. Okay. According to the standard model, what are the electrons doing?
No one knows their orbits.
We don't know. The answer is we don't know. We can only calculate what the probability is of finding them in different places, but we don't know what they're doing, what paths they're doing, or anything like that. So, it sounds like ignorance. The actual theory is that it's unknowable. It's not just ignorance, it's unknowable. Okay, so this was my page to remind us of what the importance of this all is. Because, you can get really bogged down. We went through all these models of the atom, and you're like, why? And then we talk about the absorption, the emission. It starts to make more sense if you can see light. But the key is so we can understand how light is absorbed or emitted. So now I'm going to end today by talking about the features of light. Interesting thing about light, we're scientists here. The process of understanding light has gone through a very convoluted and twisted path. So the earliest model of light that I have read, which I just find humorous, is the tentacle theory. That says that we have tentacles that come out of our eyes and touch things, and that's how we see. And I find it very funny because I just think, okay, whoever came up with that, what did he say would happen if I went like this? Do I just blind somebody because I cut off all their tentacles? That doesn't make any sense to me. But, somebody's trying to explain how we see, and back in the time they thought you had to touch things to know about them, so we must have something from our eyes that's touching things. Well, then came along the idea that light is a particle, that light is something like BBs, and those BBs fly at us, and our eyes receive those BBs and interpret those BBs. And so that was the idea that Newton believed. He called it the corpuscular theory. We have these little corpuscles of light flying through the air. But then Sir Thomas Young did an experiment on light that said it couldn't be particles. Well, specifically, what he did was he made two slits. So you have a mass that just has two slits in it. And then he shone light on those slits. And if it was BBs behind the slits, you would have just had two mounds, one for each slit. But instead, he found a pattern that went like this with a whole bunch of mounds. And the spacing between the mounds got farther apart when he made the slits closer together, and the spacing got closer together when he made the slits farther apart. Well, that's not what BBs would do, but that is what a wave would do. It's called interference. A wave, if you have a wave like a water wave, and you have two openings, the wave will go through both openings, right? And then when the wave goes through both openings, the waves continue on the other side, and the wave that went through one, the wave that went through the other, will meet up and add together what we call interference. And so Thomas Young's experiment said, light's behaving like a wave, not at all like a particle. And so everybody said, huzzah, new information. We now know that light is a wave. And so if light is a wave, then you define it by how far does it travel before it repeats. We call that distance the wavelength. So waves are going like this, and the distance for it to repeat is the wavelength. Also, the waves are repeating in time, and so we can talk about the frequency. How many times per second does it repeat? So we have two important parameters we talk about. The first one here, the wavelength, which is the distance between crests of waves, and it's denoted with the symbol lambda. That's the Greek lowercase l. L for length. Then we have the don't have the frequency yet. Let me just write here. The frequency is the number of cycles, how many times it repeats per second. We have a special unit for this, the hertz. 1 hertz is equal to 1 cycle per second. So we have the frequency or the wavelength. So here is the spectrum of light shown in wavelengths. I said the spectrum of light. James Clerk Maxwell showed that electromagnetic waves are the same thing as light. And so we have electromagnetic waves going from very long wavelengths to very short wavelengths. The visible spectrum is just a small part of that electromagnetic spectrum. So visible light, that's the only thing that's truly light because it's what we can see. But the same thing that makes light is that entire spectrum. So if you're using your cell phone is using microwaves, which inconveniently enough are not shown here. But the microwaves are, I believe, trying to remember this, I think the microwaves are somewhere around this region. But it's using electromagnetic radiation. By the way, that reminds me, the new iPhones were announced today. Yeah. They are indeed waterproof. They indeed do not have headphone jack. Just in case you're like me and going to drop, well, $650 for the 32 gig model. I don't know, but I assume $750 for the 128 gig model. There's nothing in between. Okay, so coming back to this. This is our spectrum of light. I have to stop here, but notice that light goes from around 4 times 10 to the minus 7 meters, or as we like to say, 400 nanometers, since nano means 1 billionth, to around 750 nanometers. That's the visible spectrum. So we'll talk about light more on Friday. I'll have my demonstrations out. We'll have a grand time.